What we want to do is we want to take the Laplace transform of periodic functions. Alright, so I think we all know what a periodic function is, right? If you take the graph of a periodic function, then the graph is going to essentially repeat itself, right? And it's going to repeat itself for each period, right? So here's an example of a graph that, okay, your period is from over here. Well, your period is in terms of x, right? So your period is a length over here, right? Indicated by a red arrow. Right? And you're seeing that the graph is repeating itself for each period. Okay. Right. Okay, so our definition of a periodic function, we will use this as our definition of a periodic function, right? So you have some function, right, that's going to be defined for all time t, right? And it's periodic if there is some number big T, right, such that f of t plus big T is equal to f of t, right? Right. Okay, so let's see if we could understand what this statement is graphically, right? Okay, so an example of a small f is this small f over here, which is just sine, right? And okay, so this is just small f over here, which is the sine, right? Now, what small f of t plus big T, what that would mean is for a positive t, that would mean that you're going to take your function and you're going to shift it to the left, right? And you're going to shift it to the left by the amount specified by this period over here, which is big T, right? Now you want to notice that if you shift this function over here and the period is 2 pi and you shift it by 2 pi to the left, what's going to happen is that this piece over here will fall back on itself, and in fact the entire graph will fall back on itself, right? Okay, and falling back on itself means that the graphs are going to be the same, and that is indicating that your function values are actually the same, right? So when you translate the function over here by big T to the left, right, the function is just going to get you back what you had from before. Okay, so that graphically explains why this side over here, which is translation, is equal to the original function. So for this example here, the f of t, small f of t, this statement here specifies that the small f is periodic and it has a period of 2. Okay, so you compare to this statement. Once you see this statement over here, it's saying that the function is periodic with period big T. So in this case, your function over here, the small f, is periodic with period 2 here, right? So we expect it to be periodic, and what we want to sketch this function, right? Now how you're going to sketch this function is you first sketch it here, right? And you want to notice the length of this, where it's piecewise defined, is from 0 to 2, right? So it's in fact defined on your starting period, if you want, from 0 to 2 over here, right? So if you're going to sketch these, first thing you want to do is you want to sketch from here to here, right? Alright, okay, so I drew it separately over here, right? So this part over here, where notice, as I said before, right, this is where f is defined on your first period, if you want, from starting from 0 to 2. So the length of the interval here is 1 over here and then 1 over here 2, right? Okay, so if you want to sketch this, first you sketch on your initial period or your base period if you want, right? Okay, and all you're doing is just using your piecewise definition. So between 0 and 1, the function is equal to 1, and then between 1 and 2, the function is equal to 0, right? Okay, so first what you do is you sketch your base period here, right? And now this tells you that your function is periodic, right? So what you do is, and it's periodic of period 2. So what you do is you take this base period and you basically draw copies of it, right? in this direction, and you can draw also in this direction also, right? So taking this and repeating gives you, so this piece here is a repetition of this what we draw in the base period, and likewise over here on this side, this is a repetition of what we drew on your base period here, right? Okay, so sketching these are not hard, right? What's given over here is typically the behavior of your function or the definition of your function on the base period. So first you sketch that, okay, like this. And then what you do is you just repeat the graph for a couple periods, and your period here is specified by this value, right? So in this case, the big T is equal to 2. Right. Okay, so let's look at our next example of sketching a periodic function. So your definitions over here is similar to the definition in the previous example. Here, once you see this, this is telling you that your function is periodic, right? And this value over here, the period, which is big T, is equal to pi, right? So your period is equal to pi, right? And now what you do is you sketch your initial period or your base period, right? And notice this function over here is specified for your base period, which is 0 to pi. So you sketch that, right? So sine t, right, between 0 and pi, it will start at 0, go up to 1, and then come back down to 0, right? So this is the graph of your function on your starting period or your base period, right? And now what you do is you use the fact that it's periodic, and in order to graph, you take this piece here and you just repeat it, right, for each period, right? So you take this piece here and you shift it along, and you get this piece from pi to 2 pi. Similarly, you could shift it along and get a piece from 2 pi to 3 pi. And you could also shift this way to get the piece of the graph from minus pi to 0. Right. Okay, so you want to notice both these examples are sort of standard examples that you may see in electrical, right? This periodic function, it is a square wave, right? So it is non-zero over here, goes back to 0, and then goes back up to your previous value, right? Okay, so that's your periodic behavior of your square wave, right? Each of these squares here, right? And here what we have is a rectified sine wave, right? Your rectified sine wave, what that is it just means that you take an absolute value of the sine, so where it's negative over here, it's going to reflect in your horizontal axis and come up over here, right? Okay, so your normal sine would probably would be down here, and rectified means that we're going to reflect on top over here, right? At least rectified in this case. Sometimes when you rectify, you'd keep this pulse, this part over here, and you'd make from pi to 2 pi, you'd want that flat at 0, right? Okay. And there's an example in one of the videos that I posted where you calculate Laplace transform in that case. So where this is your normal sine, and then from pi to 2 pi, it's 0. Okay. Right. Okay, so this is a method of calculating Laplace transform for periodic function, right? It's a particular formula, right? Okay, so if you want, you know that is a function is periodic, right, with your period t, right? This is going to be the form of your formula. Notice you have 1 minus an exponential with an s over here, and this coefficient big T is your period, right? And on the top here, this is not your usual integration, right? It looks like a definition of the Laplace transform, but the definition of the Laplace transform is from 0 to infinity, right? What I have over here is from 0 to t, right? So essentially what you're doing is, if you want, you could think that all you're doing is just considering the behavior on your first period, right? From 0 over here to big T over here, right? And that is all that you integrated. Right? Now, equivalently, this formula you can express this way, right? So this is using heavy sides, and doing it this way is going to be most of the times easier than doing this, because the integration here can get a little difficult, right? And there's an example in one of the videos that I posted where you actually do this integration with the exponential and there's a sign over here, right? And that actually is a fair amount of work to do because you'd need to use integration by parts twice and so, right? Alternatively, if you had the same example and you decided to do it this way, it would be easier with your heavy sides, right? Okay. All right, so the proof of this is in the notes over here. I'm not going to go through that proof, but what I do want to justify is why this top over here is the same as this top over here. So why your numerator over here is the same as the numerator, right? Notice the denominator is the same as the denominator. So in order for both of these expressions to be equal, your top here has to be equal to the top here. Right. Okay, so the justification is here, but I rewrote it, right? This has a little more detail, right? Okay, so what I'm looking at is I'm looking at this expression which 1 minus heavy side, right, where this big T is the period, right? Okay, so if I forget about the f of t for the time being and I just consider the 1 minus heavy side, right? You want to remember what 1 minus heavy side looks like, right? We talked about this, right? Your 1 minus the heavy side is going to be 1 between 0 and this value over here, big T, and then it's going to be 0 afterwards, right? So 1 minus heavy side is 1 between 0 and big T, and then it's going to be 0 after the big T, right? Now, what I have over here is 1 minus the heavy side times f of t, right? So what I have is 1 minus the heavy side times the f of t, and now I consider this, right? Okay, so I want to consider this for your two intervals that's specified here, right? And for the two intervals that's specified here, this is a product, right? It's a product of the 1 minus the heavy side times the small f, right? And on this interval 0 to big T, the 1 minus heavy side is equal to 1, right? So what I'll have is 1 times f of t, which is just the f of 1 times f of t will just simply give me f of t, right? And then after big T, this 1 minus heavy side is equal to 0, right? Like the 0 there, right? And so on this interval here after T, 1 minus heavy side is 0, and 0 times the small f would just be 0, right? Okay, so what that tells me is that the 1 minus the heavy side times the small f, I can express this way as a piecewise defined function, right? Where it's going to be small f of t between 0 and big T, and it's going to be 0 afterwards, right? And this we actually saw before, right? If you have something that's piecewise, at least, but we did it in the next way, right? If you have something that's piecewise defined, we can express it in terms of heavy sides. Okay. Right. Okay. So now that I have this, what I want to do is I want to show that Laplace of 1 minus the heavy side over here times f of t is in fact so that the 1 minus the heavy side, this top over here, is equal to this, right? Okay, so Laplace of 1 minus this expression of 1 minus heavy side times small f is taken Laplace of this function, but this function is piecewise defined, right? Anyway, so I've taken Laplace of this function, right? And I use the definition of the Laplace transform, which means it's exponential e to the minus t, st, right? Times my function over here inside my square brackets. Okay, so I'm integrating between 0 and infinity, but this function has two types of behavior, one from 0 to big T and one from big T to infinity. So what that means is when I'm integrating from 0 to infinity, I'll split this integral into two pieces, 0 to big T and then T to infinity. Right. So from 0 to big T, this function here is equal to f of t, so I put that in. And then from big T to infinity, your function is equal to 0, and I put that in, right? This is integrating 0, so this will drop off, and I get this expression, right? And what you want to notice now is Laplace of 1 minus the heavy side times the small f is equal to the integral between 0 and big T of exponential times small f, right? So that's what I wanted to show, right? So that explains why this expression is the same as this expression over here, right? All right, okay, so let's do an example of sketching a periodic function and taking the Laplace transform of the periodic function, right? Okay, so given this function over here, this entire thing specifies the function, and you notice you're given this here, and this piece over here tells you that the function small f is periodic with period 1 over here. So the big T is equal to 1, right? Okay. So this tells you it's periodic, and this part over here tells you what the behavior is, what the function is defined as on your initial or your base period, right? Okay, so in initial or base period between 0 and 1, the function is equal to t, and t is simply a straight line passing through the origin of slope 1, right? Okay, so that between 0 and 1 is just a straight line passing through the origin, slope 1, right? This diagram probably could be a little better, so I should have a closed dot over here and an open dot over here, right? Okay, so between 0 and 1, I sketched the graph on your base period, right? And now to sketch the rest of the graph, I just use the fact that it's periodic with period 1, so this here is just going to repeat for each period, right? So here, this piece is between 0 and 1, right? And it's going to now repeat between 1 and 2, right? And then it'll also repeat between 2 and 3. And on this side over here, it'll repeat between minus 1 and 0. Right. Okay, now what we want to do is we want to get Laplace transform of your periodic function, right? And to get Laplace transform of your periodic function, what we're going to do is we're going to use this formula here, right? As I said, this one is a little harder to work with because you need to do your integration over here, but this one is easier because you could really just use formula, right? Okay, so I'm going to use this one here, right? Right. Okay, so let's just work out the top for the time being, right? And then eventually we'll put in the bottom here. Okay, so you're working out the top. It's 1 minus heavy side, right? You have 1 over here because that's your period. And then your function small f here, right? Now, this over here, what you're doing is you're looking at the function just between 0 and 1, right? Because 1 minus your heavy side over here, all you're doing is you're just picking up the behavior, right, from 0 to 1, right? Okay, so when you put in what the f of t is, all you're doing is you're just using the small t here. Okay, so the small f is equal to t, and now we want to work this out, right? And this is just going to come straight from eventually with this over here, you're going to expand it out and really just use formulas, right? Right. Okay, and the formula that we will use is this t-shift formula over here to work out your Laplace transform, right? If we need to. Right? Okay, so I want to work this out, and what you do is, well, it's 1 minus heavy side times t, so you expand, right? So you get t times 1, and then ht minus 1 times t, right? Okay, now I come to this situation with this ht minus 1 times t, right? Now, ht minus 1 times t, right? What you do want to notice is that this actually is not exactly in this form here, right? If you have this form over here is heavy side t minus t0 and then y t minus t0, right? So this is shifted over here, and you want this to also be shifted in order for this formula to work, right? Okay, so once you get to this point, you have two ways to do this, right? You could either use this formula, or you could use this one over here, which is in fact probably easier in this case, right? But let me first do it this way, right? Okay, so I'm working this out, right? And the problem over here is the ht minus 1 times the t, right? Now, in order for this formula over here to work directly, right, what I would want this to be is I'd want this to be t minus 1, right? But it isn't quite t minus 1, it's t, right? But you could do a little algebraic manipulation over here, right? And you notice that t is equal to t minus 1 plus 1, right? The plus 1 here will cancel with the minus 1 to just give me back to t, right? So all I did is write this t as in terms of t minus 1, right? And once I do that, I can expand out and I get t minus h t minus 1 times t minus 1 minus just a heavy side. And you use your linearity to break this up. Laplace of t is going to come straight from the table. Laplace of this here is going to come from using this formula, right? And then I have Laplace of just a heavy side by itself, right? Now Laplace of a heavy side by itself is e to the minus s on s, right? And Laplace of heavy side times t minus 1, right? If I'm using this over here, right? Okay, so I'm looking at this and I want to use this formula, right? Right, I have t minus 1 here, so that would correspond to having, say, a t minus 1 over here. And then when you come across on this side, you unshift, right? So you'll have e to the minus s, and this would be Laplace of t, right? And Laplace of t is 1 on s squared. So that's how I get e to the minus s times the 1 on s squared there, right? Okay, so that works it out for me here, right? So that is the top of this formula, right? And now I need to put in the bottom, right? So the bottom is e to the 1 minus e to the minus st. The big T is 1. So this is 1 minus e to the minus s. And this is my denominator. And what I worked out from before is the numerator, right? Okay, there isn't a huge amount that you could do here for simplification. You'd want to clean this up. So what you do is you take a common denominator here, which is s squared. When you take a common denominator here, which is s squared, right, you end up with an s hitting this e to the minus s, right? Okay, and that common denominator, which is s squared, will come down on the bottom here, right? And then the s e to the minus s is, that is, okay. Okay, so once you have the s squared that comes down like this, what you're left with is just your top over here, right? When you took your common denominator, and that would have been 1 minus e to the minus s times your s here. And here what you do is you factor out your e to the minus s to get the 1 plus s. Right? Okay. Right, so that the issue over here is working out this top here, right? Okay, so let's do it the next way, right? And probably it may be easier for you all, right? Why it would be easier? Because going from here to here, where you needed to express the small t in terms of small t minus 1, right? To think of that and to try to figure that out, that might raise some issues. So the second way, we don't really need to do that, right? And to avoid doing that, what you're going to do is you're going to just take an equivalent form of your t-shift, but now stated in this way, right? Okay, so here, well, what's going on over here, right? Here, this is, when you look at this is y, where it's shifted by t0. And here, what you do is you unshift, right? Now you want to notice when you unshift, how you go from here to here is you add t0, right? And you effectively doing the same thing in this formula, right? Here, if I just have yt, right, to go from here to here, you add t0, okay? Right. So this is an equivalent form of this t-shift formula, and it turns out that this one is sometimes easier to use when you're doing your problems, right? Okay, right. So let's work out the same Laplace transform here, but now doing it using this formula. Okay, so I have Laplace of 1 minus Heaviside times small t. I expand it out. Okay, and I get Laplace of t times Laplace of ht minus 1 times t, right? So I get the same thing so far, right? But now what I'm going to do over here is I'm going to use, instead of trying to express this t in terms of t minus 1, I'm just going to use this formula here directly, right? What it's saying is to work this out, right? You're using this exponential e to the minus s. This number over here is going to come from the heavy side, the t0 here. And t0 is equal to 1, so the coefficient here is now 1, so I get the e to the minus s. And your y of t is going to change to y of t plus the t0, right? So in this case, this is the y of t, and this will shift from t to t plus 1, right? So that's how I get this. Okay, so notice going from here to here, you don't have to think about expressing the small t in terms of t minus 1 and so. This is a little more straightforward, right? So using this formula here, I get from t to t plus 1. And now this is just normal Laplace transform, right? So Laplace of t is 1 on s squared, and Laplace of 1 is 1 on s. And I end up with what I had from before, right? And what I had from before will give me my answer, the same answer again, right?